The universe has a size, but it is a size we may never fully grasp. Not because it is too large to measure, but because parts of it are forever beyond our ability to observe. If you step outside on a clear night, the Milky Way may appear immense, a quiet river of light stretched across the sky. Yet what you see is only a small component of a much larger structure. To understand scale in cosmology, we must begin not with objects, but with boundaries defined by physics. The observable universe is the largest region from which light has had enough time to reach us since the beginning of cosmic expansion. This is a crucial distinction. It is not the entire universe. It is only the portion accessible to observation. Now consider a simple idea. Light travels at a finite speed. This means every observation is also a look into the past. When we observe distant galaxies, we are not seeing them as they are today, but as they were when their light began its journey. Here is where the numbers require careful interpretation. The universe is approximately 13.8 billion years old. One might expect the observable boundary to lie at 13.8 billion light-years. However, space itself expands. While light travels toward us, the distance it must cross also increases. As a result, the observable universe spans roughly 93 billion light-years in diameter. This is not an edge in the conventional sense. There is no wall, no boundary one could approach. Instead, it is a horizon defined by time, expansion, and the speed of light. At this horizon, we do not encounter galaxies. We encounter a faint, uniform glow known as the cosmic microwave background. This radiation originates from a time about 380,000 years after the universe began, when matter cooled enough for light to travel freely. Before this moment, the universe was opaque, and light could not move without constant interaction. A useful way to think about this is to imagine fog gradually clearing. As visibility improves, deeper layers become observable. The cosmic microwave background represents the earliest layer we can currently access. A brief teaching insight. The limitation here is not technological, it is fundamental. No matter how advanced our instruments become, we cannot observe beyond this boundary using light, because no earlier light exists that can reach us. This leads to an important conclusion. The observable universe is a measurement of our perspective, not the full extent of reality, and beyond this horizon there is no clear map, only unanswered questions about how the universe behaves on scales we cannot directly see. People often imagine the universe as something vast but still stable, as if galaxies simply sit within it like distant islands. The reality is far less intuitive. The universe itself is in motion, continuously expanding, carrying galaxies like the Milky Way along with it. Beyond that observable horizon, the next step is not to look farther, but to understand how the universe itself changes over time. The universe is not static, it expands. This statement may seem simple, but it requires careful interpretation. Expansion does not mean galaxies are moving through empty space away from a central point. Instead, space itself is stretching. The distance between galaxies increases because the fabric that connects them is continuously growing. A useful way to visualize this is to imagine points drawn on the surface of an inflating balloon. As the balloon expands, every point moves away from every other point, not because they are traveling across the surface, but because the surface itself is stretching. Importantly, there is no special center on that surface. In the same way, the universe has no preferred central location. In its earliest known phase, the universe underwent a brief but extremely rapid expansion known as inflation. This occurred within a fraction of a second after the beginning and expanded space at a rate far exceeding what we observe today. A teaching insight here is that inflation helps explain why the universe appears remarkably uniform in all directions. Regions now separated by vast distances were once much closer and could share similar physical conditions. As time progressed, gravity began to slow this expansion. Matter pulled inward, resisting the outward stretch. However, observations in the late 20th century revealed something unexpected. The expansion did not continue slowing indefinitely. Instead, it began accelerating again. This acceleration is attributed to what we call dark energy, a form of energy that permeates space itself. Its exact nature remains unknown, but its effect is measurable. It pushes space to expand faster over time. The primary evidence for expansion comes from redshift. Light travelling through expanding space is stretched, increasing its wavelength. The farther a galaxy is, the more its light is shifted toward the red end of the spectrum. This relationship allows us to measure distance and, importantly, to look back in time. A brief clarification. When we observe a galaxy billions of light years away, we are seeing it as it existed billions of years ago. Distance in cosmology is directly linked to time. The universe, therefore, is not only expanding in space, it is evolving through history, with every observation revealing a different stage of its past. As this expansion continues, it does not leave matter unchanged. Instead, it sets the stage for the next level of organization, where gravity begins shaping matter into patterns across vast scales. As expansion continues to stretch space, it does not leave matter evenly spread. Instead, it begins to organize it. At the largest scales, the universe develops a structure that is both simple in principle and complex in appearance. Matter is not scattered randomly. It forms an interconnected network known as the cosmic web, composed of long filaments, dense clusters, and vast empty regions called voids. To understand how this structure forms, we begin with a subtle detail from the early universe. After inflation, matter was distributed almost uniformly but not perfectly. There were tiny variations in density, differences so small they would be difficult to detect without precise measurement. Yet these small differences are crucial. Gravity amplifies them over time. Regions that are slightly denser attract more matter, becoming even denser. At the same time, regions that are less dense lose matter and grow emptier. This process continues over billions of years, gradually transforming a nearly uniform universe into one with a distinct pattern. A helpful way to think about this is to imagine rainwater collecting on uneven ground. Even a slight dip gathers more water, deepening the depression and drawing in more flow. Similarly, small initial variations guide the large-scale distribution of matter. An important teaching insight is that visible matter alone cannot account for the structure we observe. The majority of the gravitational framework is provided by dark matter, an invisible component that does not emit or absorb light. It forms the underlying scaffolding, while galaxies develop along its structure like beads arranged along threads. Between these filaments lie voids, enormous regions containing very little matter. Some span tens of millions of light years. These are not gaps created later, but natural outcomes of the same process that forms clusters. The result is a universe that appears uniform when viewed at the largest scale, yet highly structured when examined in detail. Both descriptions are correct, depending on the level of observation. This pattern is not random. It is the direct consequence of simple physical laws acting over immense spans of time. And within this vast network, the next level of structure begins to emerge, as matter gathers more tightly to form gravitational systems that we recognize as galaxies. Within this vast cosmic web, matter does not remain spread across filaments indefinitely. Over time, gravity draws it inward, concentrating it into more compact and recognizable systems. These systems are galaxies. A galaxy is not simply a collection of stars. It is a gravitational structure that holds together stars, gas, dust, and a much larger component of dark matter. Each of these elements plays a role, but it is gravity that maintains the system as a whole. The observable universe contains hundreds of billions of galaxies, and this number may be an underestimate. Advances in deep sky observation continue to reveal faint systems that were previously undetected. A useful teaching insight here is that even our best measurements improve with better instruments, reminding us that our cosmic inventory is still incomplete. Galaxies vary significantly in size and form. Some are spirals, with rotating disks and well-defined arms. Others are elliptical, appearing more rounded and lacking clear structure. There are also irregular galaxies, which do not follow a simple pattern. These differences arise from formation history, interactions, and internal dynamics. To understand scale, consider this comparison. A large galaxy may contain up to 1 trillion stars, while smaller dwarf galaxies may contain only a few million. Yet both are considered galaxies because they are bound systems shaped by gravity. The Milky Way is one such system. It is classified as a barred spiral galaxy, with a central bar-like structure and extended spiral arms. It contains hundreds of billions of stars and spans roughly 100,000 light-years across. These numbers may seem large, but in the broader cosmic context, they are typical rather than exceptional. An important clarification is that no single galaxy dominates the universe. Even the largest known galaxies are part of a much wider population. The Milky Way, despite its scale from our perspective, is simply one member among countless others distributed across the observable universe. This realization shifts our understanding. What appears vast on a local scale becomes ordinary when placed within a larger framework. To properly understand the Milky Way, we must now narrow our focus. Rather than comparing it to the entire universe, we begin examining the structures immediately surrounding it, where gravitational relationships become more direct and measurable. When we narrow our focus from the vast population of galaxies, a new pattern begins to emerge. Galaxies are not randomly placed. They gather into larger regions, forming structures that define their cosmic neighborhoods. One such structure is known as a supercluster. This is not a tightly bound system like a single galaxy, but a broad region where many galaxy groups and clusters are concentrated. The Milky Way exists within one of these regions. Traditionally, this region has been identified as the Virgo supercluster, named after the dense cluster of galaxies located in the direction of the Virgo constellation. However, more recent studies have refined this picture. By tracking the motion of galaxies rather than just their positions, astronomers have identified a larger structure called Laniakea. A useful teaching insight here is the difference between defining structure by location and defining it by motion. When galaxies are mapped by where they are, we see clusters and groupings. When they are mapped by how they move, we uncover larger flow patterns shaped by gravity. Laniakea is defined in this second way. It is a region where galaxies share a common flow toward a gravitational center. This distinction is important. Superclusters are not fully bound systems. Over very long timescales, cosmic expansion can overcome their internal gravity, causing parts of them to drift apart. What we observe is not a permanent structure, but a dynamic one, evolving over billions of years. The Milky Way does not sit at the center of this structure. It occupies a relatively quiet position in the outskirts, away from the densest regions. This placement has consequences. It influences the types of interactions our galaxy experiences and the overall stability of its environment. To understand scale, imagine a city within a country. The city may be large and complex on its own, but it is still only a small part of a much broader system. In the same way, the Milky Way is one galaxy within a supercluster, shaped by forces that act far beyond its immediate boundaries. This broader context is essential, but it is still too large to fully understand the Milky Way's direct interactions. To see those more clearly, we must move closer, into a smaller and more tightly bound system where gravity plays a more dominant role. From this broader supercluster environment, we now move into a scale where gravity begins to act more directly and predictably. Here, the structures are smaller, but far more tightly connected. This region is known as the local group. Unlike superclusters, the local group is a gravitationally bound system. This means its member galaxies are not drifting apart with cosmic expansion in the same way. Instead, gravity dominates, holding them together as a coherent structure. The local group spans roughly 10 million light-years and contains dozens of galaxies. Most of these are small dwarf systems, faint and difficult to observe. However, two galaxies dominate this region, the Milky Way and the Andromeda Galaxy. These two systems are comparable in size and mass, and their relationship defines much of the local group's dynamics. They are not moving apart. In fact, they are moving toward each other. A useful teaching insight here is that cosmic expansion does not act uniformly at all scales. While distant galaxies recede from us due to expanding space, gravity can locally overcome this effect. In bound systems like the local group, gravitational attraction is strong enough to reverse the outward motion. As a result, the Milky Way and Andromeda are on a collision course. This interaction will not occur immediately, but over billions of years the two galaxies will merge into a single, larger system. Such events are common in cosmic history and play a major role in galaxy evolution. Surrounding these dominant galaxies are smaller companions. These dwarf galaxies orbit them, influenced by their gravitational pull. Some remain stable, while others are gradually disrupted, stretched, and absorbed over time. To understand this scale, consider a simple comparison. If the observable universe is like a vast landscape, and superclusters are regions within it, then the local group is more like a neighborhood. Interactions here are not distant or indirect. They are immediate and measurable. Within this neighborhood, the Milky Way is no longer just one among countless galaxies. It becomes one of the central systems, shaping and being shaped by its surroundings. To fully understand its true extent, however, we must now look beyond its visible structure, into regions that do not shine but still define its size. To understand the true size of the Milky Way, we must move beyond what is immediately visible. The bright disk of stars, though extensive, does not define the full extent of the galaxy. Surrounding this luminous region is a much larger and far less visible structure known as the galactic halo. The halo is not dense or brightly lit. It is a diffuse region extending well beyond the main disk, containing a sparse population of stars, globular clusters, and elongated streams of stellar material. These streams are not random. They are remnants of smaller galaxies that were gradually pulled apart and absorbed over time. A useful teaching insight is that galaxies do not form in isolation. They grow through mergers and interactions. Each stellar stream in the halo is evidence of a past event, preserving the history of how the Milky Way accumulated its mass. In addition to stars, the halo contains globular clusters, compact groups of ancient stars that orbit the galaxy at large distances. These clusters are among the oldest known structures, offering valuable information about the early stages of galaxy formation. However, the most significant component of the halo is not visible at all. It is dominated by dark matter, which extends far beyond the reach of starlight. While we cannot observe this matter directly, its presence is inferred through gravitational effects, such as the motion of stars and satellite galaxies. This leads to an important clarification. The size of a galaxy cannot be defined solely by its visible boundaries. The gravitational influence of dark matter extends much farther, meaning the true extent of the Milky Way is significantly larger than what we can see. Unlike a solid object, the galaxy does not have a sharp edge. Its density gradually decreases with distance fading into the surrounding space. The transition is continuous, not abrupt. To visualize this, consider the glow of a distant light fading into darkness. There is no precise point where it ends, only a gradual reduction in intensity. The Milky Way behaves in a similar way. By extending our view beyond visible stars, the galaxy becomes less like a defined object and more like a region of influence. And even beyond this extended halo, the Milky Way continues to interact with its surroundings, drawing in smaller systems and shaping the space around it. Extending beyond the halo, the influence of the Milky Way does not simply fade away. It continues through a system of smaller galaxies that remain bound to it by gravity. These are known as satellite galaxies. Unlike the large independent galaxies discussed earlier, satellite galaxies exist within the gravitational domain of a more massive system. They orbit the Milky Way in much the same way that smaller bodies orbit larger ones, though the scales involved are vastly greater. The most prominent examples are the Large and Small Magellanic Clouds. These are visible even to the naked eye from the southern hemisphere, and serve as clear evidence that the Milky Way is not an isolated structure. They are not distant background objects, but active members of its immediate environment. Beyond these, there are many dwarf galaxies, small, faint systems containing relatively few stars. Some are stable in their orbits, while others are gradually being disrupted by tidal forces. These forces arise because gravity does not act uniformly across an object. The side closer to the Milky Way experiences a stronger pull than the far side, stretching the galaxy over time. A useful teaching insight is that this process is not rare or exceptional. It is a fundamental aspect of how galaxies evolve. Larger galaxies grow by interacting with and absorbing smaller ones, a process that continues over billions of years. Observations of these satellite galaxies reveal streams of stars being pulled away from them, forming elongated trails that wrap around the Milky Way. These structures provide direct evidence of ongoing interaction and gradual merger. This leads to an important clarification. The boundary of a galaxy is not defined only by where its stars are located, but by how far its gravitational influence extends. Satellite galaxies mark this boundary more clearly than visible light alone. In this sense, the Milky Way is not just a collection of stars and gas. It is a dynamic system actively shaping and being shaped by its surroundings. And even beyond these companions, there exists another component, less visible but equally significant, that surrounds the galaxy and connects it to the larger cosmic environment. Beyond the influence of stars and even satellite galaxies, the Milky Way extends into a component that is far more difficult to detect, yet essential for understanding how the galaxy functions as a system. This region is known as the circumgalactic medium. It is not composed of stars or dense structures. Instead, it consists of a vast envelope of hot, diffuse gas that surrounds the galaxy at large distances. Unlike the bright disk or even the sparse halo, this medium does not emit light in a way that can be directly imaged under normal conditions. Its presence is revealed through indirect methods. When light from distant sources passes through this gas, specific wavelengths are absorbed, leaving identifiable signatures in the observed spectrum. In other cases, high-energy observations, such as X-rays, allow us to detect the hotter components of this medium. A useful teaching insight is that absence of visibility does not imply absence of matter. Much of what defines a galaxy exists in forms that are not immediately observable, requiring careful interpretation of indirect evidence. The circumgalactic medium plays a critical role in the life cycle of the galaxy. It acts as both a reservoir and an exchange system. Gas from this region can gradually fall inward, contributing to star formation within the galaxy. At the same time, energetic processes, such as supernova explosions, can push material outward, returning it to this surrounding medium. This continuous exchange means the Milky Way is not a closed system. It interacts constantly with its environment, gaining and losing matter over time. To visualize this, it is helpful to think not of a static structure, but of a system in balance. Material flows inward and outward, maintaining a dynamic equilibrium that evolves slowly across billions of years. An important clarification is that this medium extends far beyond the visible boundaries of the galaxy. It connects the Milky Way to the larger cosmic environment, acting as an interface between the galaxy and intergalactic space. By this stage, the concept of a galaxy has expanded significantly. It is no longer just a collection of stars or even a gravitationally bound structure, but a complex system interacting with its surroundings on multiple levels. To complete this picture, we now return inward, focusing once again on the structure that is most familiar, yet often misunderstood, the visible disk where most of the galaxy's stars reside. Returning now to the inner regions of the Milky Way, we arrive at the structure that is most familiar, yet often misunderstood when viewed in isolation. This is the galactic disk. The disk is the bright, flattened region where most of the galaxy's visible stars, gas, and dust are concentrated. It spans roughly 100,000 light-years in diameter, a scale that is difficult to visualize directly. Within this region, stars are not distributed randomly. They follow organized patterns that reflect the underlying dynamics of the galaxy. One of the most recognizable features of the disk is its spiral structure. These spiral arms are not fixed objects made of the same stars over time. Instead, they are regions of higher density, where stars and gas temporarily gather as they orbit the galactic center. As material moves through these regions, it becomes compressed, leading to the formation of new stars. A useful teaching insight is to think of these arms not as solid structures, but as traffic patterns. Just as cars slow down and cluster in certain regions of a highway, without remaining fixed, stars move in and out of spiral arms over time. The disk itself is not perfectly flat or uniform. Observations show that it warps and bends, particularly in its outer regions. It also becomes less dense as we move outward, gradually fading rather than ending abruptly. This reinforces an idea we have encountered before. In astronomy, boundaries are often defined by gradual transitions rather than sharp edges. In addition to its structure, the disk is an active region. It contains cold gas clouds where new stars continue to form, as well as older stars that have completed much of their evolution. This mixture of ages provides a continuous record of the galaxy's history. An important clarification is that while the disk is the most visible part of the Milky Way, it represents only one component of a much larger system. When viewed alone, it can give the impression of a complete structure. When placed in context, it becomes one layer within a hierarchy that extends far beyond it. From the scale of the observable universe down to this rotating disk, we have traced a continuous sequence of structure, each level defined by different physical processes and scales of interaction. The Milky Way, in this final view, is both vast and limited. Vast in its own dimensions, yet small when compared to the universe that contains it. And that contrast is the central insight. What appears immense from within becomes modest when seen as part of a larger system, reminding us that scale in the universe is always relative to perspective.